Good morning to all. Welcome to the course Semiconductor Device and Circuits, which is introduced in R25 regulations for the first semester. As you are aware of it, the semiconductor device is very fundamental devices in electronics world. Nowadays, we see that wherever we go, the electronic devices ruling the world. Without these devices, we cannot imagine that how the world is running. That's why this course has been introduced to the beginning of the BTech first year, the semiconductor device and the circuits. The semiconductors, already you are aware of the basic fundamentals during your 11th and the 12th standard of physics course. In continuation to that, we will see today the fundamentals of bipolar junction transistor, how it is constructed, how it's working, and the applications of the BJT. See, bipolar junction transistor, you know that bipolar, that indicates holes and electrons determine device characteristics. The holes, which are the majority charge carriers, p-type semiconductors. Electrons are majority charge carriers in n-type semiconductors, which will participate in VI characteristics. From there, we can understand that bipolar. And if you see the transistor, the name itself indicates the transistor. It's a three-terminal device controlling of two-terminal currents. Transistor, we can say that trans plus resistor. It transmits as well as it resists. That's why the name indicates the transistor. The junction, it consisting the two junctions. We have the two junctions, the transistor consisting, where the base collector junction, junction BC, and also you can see the junction BE. Basically, we called as a BJT. If you see that the transistor structures, the bipolar junction transistor has specially doped regions and contains two PN junctions. Here you can see that this is the emitter terminal, the base terminal, and the collector terminal. And here you can see that the emitter, the base, collector. This is the PNP transistor, and this is NPN transistor. There are two types of transistors. Basically, we can see NPN and PNP transistor. As we discussed, bipolar transistor is a three-terminal device. It has emitter, base, and collector. The emitter is represented as E, the base will be represented as B, the collector will be represented as C. We will see that what do you mean by emitter, what do you mean by base, what do you mean by collector. The basic transistor principle is that the voltage between two terminals control the current through the third terminal. Here you can see that the controls is very important. Nowadays we see that everything need to be in control, especially the semiconductor devices. SDCs need to be in control. If the device is not in control, we cannot imagine how the world will be. The transistor, the size nowadays is keep on reducing, keep on scaling down. The industries are using 2 nanometers, 2 nanometer length, and 1 nanometer length. Still the research is going on to minimize the channel length of the transistors. As the device is scaling down, the controllability becoming very issues. The controllability becoming a big problem. When the device is not in control, we cannot use it for several other applications. The electronic devices are mainly used for controlling. Now we can see the automation electrons, automated vehicles, everything need to be in control. That's why this fundamental course will be very helpful for you to understand that how this current is getting controlled. Between two terminals, current is controlled through the third terminal. The current, the electrons are transmitting from emitter to the collector. The base is the controlling terminal, where the current is traveling from emitter to the collector. The base plays very important role to control this flow. The current in the transistor is due to the flow of both electrons and the holes, hence the name is called bipolar. Now if you see further, the transistor are three-terminal device made from different semiconductor materials that can act as either an insulator or conductor by the application of small signal voltage. The transistor ability to change between these two states enable it to have two basic functions such as switching, which comes under the digital electronics, or the amplification, which comes for the analog electronics. The switching is very important because as we are operating the devices with the high speed devices we want, in order to the high speed, the switching frequency has to be very high. Where we can see that another one, the amplification, where the input signal is very small, we want to amplify that into the become very big signal in terms of the amplitude, in terms of the frequency. So here the basic applications of BJT is switching and the amplification. As you go for the higher studies, you will understand that the digital electronics, the course will study separately, and the analog electronics course also will study separately. These are the very essential topics. If you recap PN junction, how it works, here you can see that the illustration, the simple here, as we studied earlier, the PN junction, when p-type semiconductor, n-type semiconductor connected together. In between p-type semiconductor and n-type semiconductor, the junction forming. Here we can see that here the junction is having the width of W. As we discussed, the p-type semiconductor having the majority charge carries the holes, n-type semiconductor majority charge carries the electrons. And here we applied the positive voltage, which is greater than 0. And if you see that the 4 bars, when we say PN junction is in 4 bars, the positive supply is connected to the P side and the negative voltage is connected to the N side. The all holes to jump over the barrier into the N region as the minority charge carriers. If you see the another picture, there you can see that the applied voltage is less than 0. That means here the p-type semiconductor we have given the negative supply, whereas here the N side we have given the positive supply. If you observe these two pictures, here the width is W and here is also width is W. You can see that the how much width you can see here. If you see the comparison, the width becoming large, that's we can observe in the reverse bars. During the PN junction reverse bars, the depletion width is becoming larger, whereas PNP diode, the first 4 bars, the depletion width is narrow. Here you can see that how the transistor is forming. We studied already the 4 bars VA characteristics. Voltage is the x-axis, current in the y-axis. After the cut in voltage, the current is increasing exponentially. Now you can see that during reverse bias, try to see that the animated picture here. You can see that the picture how during the reverse bias, the electrons are going away from the barrier, holes are going away from the barrier. Hence, the depletion width is becoming higher and higher. That's why we got it the VA characteristics like this. The reason behind is that very negligible current is there initially. After the breaking down, after the breaking of the barrier, the large current is flowing through the PN junction diode. And by understanding this PN junction diodes, reverse bias and the forward bias, here the formation of the BJT can be easily understood. You see that here P-type semiconductor, N-type semiconductor, there the N-type semiconductor and the P-type semiconductor. Now here we have the positive voltage and here we have the negative voltage. With this basics, you can see that the animation picture how these are combined. Now you can see that PNP transistor is forming. PNP transistor is forming. I am repeating again here. You can see that this is the way the formation of PN junction. The first reason is in forward bias where we have seen it, and the second reason is in reverse bias. Holes from the P region will emit. That's why we call the terminal name is emitter. Holes from the P region, emitter of the first PN junction, driven by the forward bias of the PN junction into the central N region, which is we call as base. Further, holes driven by the reverse bias of the second PN junction from the base region into the P region of the second junction is called collector. The simply you can see that here emitter will emit, the base will pass, the collector will collect. The simple understanding of these three terminals: emits, pass and collector. Now you can see that the animated, the holes how it is moving from the which are in P-type semiconductor at the left side of the BJT. It's moving to the base and the base to the collector, right? This is the way clearly you can understand that how this BJT works. And if you see that the current flow in the opposite direction of the electrons flow, the same direction as holes. This is the electrons moving, the current direction is opposite of electrons, the same as the holes. This you need to understand. And also here you can see that the bipolar junction transistor is a current control device. As I told in the beginning of the slide, the device is a control device. Now here we can see the current will be controlled. Two terminals current is controlled by third terminal. You can see that the IE current is entering, IB is leaving, the IC is leaving. This is the PNP transistor. Whereas NPN transistor, we can see that the collector current is entering, the base collector is entering and the emitter current is leaving. This is another symbolic representation. You can see that the voltage representation, the voltage between the base and the collector we represent as a VCB. The voltage between the base and the emitter we represent as a VEB. The voltage between the emitter and collector is the VCA. Similarly, for the NPN transistor, you can see that the NPN transistor, the arrow mark is coming out. When the arrow mark is coming out of the transistor, we call it as a NPN. Whereas arrow mark is going in to the transistor, we call it as NPN transistor. Easily can distinguish between these two transistors. Here also the voltage we see that VCB, VEB and the VCA. Above picture we can see that the current notations. This picture we can see that the voltage notations. If you apply the KCL, Kirchhoff current law, to a transistor, we can see the relation I is equal to, right? Here you can see that the I is equal to IB plus IC. The I is, if you see the NPN transistor, I is leaving. The all leaving currents is equal to the entering currents. Or else algebraic sum of the currents in a node is equal to 0. Or else you can say that the entering current is equal to the leaving currents. From that we can understand that the I is the entering current and the IB is the leaving current, IC also leaving current for the NPN transistor. This is the KCL for the transistor. And also if you apply the KVL to a transistor in a loop, algebraic sum of the voltage is equal to 0. There you can rewrite VEC is equal to VEB plus VBC. If you see that, distinguish the three terminals, we can understand that the emitter is highly doped because its job is to emits or inject electrons into the base. In order to emit, it should have heavily doped electrons. Excess number of charge carriers has to be present. The base is lightly doped and generally it is very thin because the base job is to be just pass the electrons. That's why it is lightly doped. And the doping level of the collector is intermediate between the emitter and the base because it has to be collect the charge carriers. And if you see the area wise, the collector has to be collect, that's why it should have the larger area. Among all these three, collector has the larger area compared to the emitter and the base. Base is very thin, emitter region is moderate in size. The cross section of the BJT indicates that the collector base junction has much larger area than the emitter base junction. If you see that the talk about the collector base junction and the emitter base junction. The bipolar junction transistor, unlike other transistor, is usually not a symmetrical device. Whereas the MOS transistor, where you have the source and the drain, the gate, source and the drain. Source can act as a drain. Drain also can act as a source. But whereas the BJT, the base, collector and the emitter, you cannot interchange collector as the emitter as a collector. You cannot do that. That's why it's said to be, it's not in a symmetrical device. Whereas MOS transistor is a symmetrical device, but the BJT is not a symmetrical device. You need to understand this terminology. It's very important for you. If you see the summary of this, the terminals, the emitter is in terms of the doping, emitter is highly doped in order to emits. The base is low dope, just a pass. Collector is intermediately doped. Whereas area wise, if you see, the collector area is large. Why? Because it has to collect, it has to store, it has a storage capability. Whereas emitter is medium and the base is very thin. If you see in terms of the job, what is the emitter job? What is the base job? What is the collector job? The emitter job is to be emit, base job is to be pass, the collector job is to be collect. Simply you can remember by one word. We have seen that. And also for the realization, you can see that the two diodes connected back to back. Here the representation, you can see that NPN transistor, one diode and the another diode. Two diodes are connected back to back. And here also you can see that PNP transistor. This is the way we can understand that the BJT, construction of the BJT. To identify the three regions of operations, right? You can see that simply here. The transistor is going to be operated in 4 regions. Among 4 regions, we will use for the 3 regions mostly. The active region. What do you mean by active region? What do you mean by active region? The active region means that the base emitter junction, right? The B junction. The B junction has to be in forward bias, whereas the BC junction has to be in reverse bias. So that we can use the transistor as an amplifier. During the active region of the BJT, the transistor is going to be operated as an amplifier. There we can see that the IC current is the output current, whereas IB current is the input current. The output current is equal to beta times of input current. The beta is the current gain factor. We can understand that here. The beta is equal to IC by IB. The beta generally varies between 50 to 250 for a transistor. And you can see that another reason, the cutoff region. Both the junctions are in reverse bias. You can see that here is in reverse bias. Here also will be in reverse bias. BA junction and the BC junction. When both the junctions are in reverse bias, the transistor is said to be in cutoff region. There is voltage but little current. Hence we call it as a transistor is off. The current flowing through the IC, the output current will be 0. Sometimes the leakage current come into the picture when the device is in cutoff region. Third region we will see that the saturation region. The saturation region indicates that the base emitter junction is in forward bias and the base collector junction is in forward bias. Both the junctions should be in forward bias. The transistor is said to be saturation region. There is a little voltage but lot of current. You can see the transistor is fully on, where we can see that the IC is equal to IC SAT. IC is equal to IC SAT. And the fourth one we can see that BC junction is in forward bias and B junction is in reverse bias. The transistor is said to be in inverse active. During the inverse active, the transistor is going to be operated as attenuator, opposite of amplification. The active region, amplifier, and cutoff region, saturation region, you can say that the switch. These are the 2 important applications of BJT. If you see further, this is the way you can see that illustrations. The green indicates forward bias, the red indicates the reverse bias. Both are in forward bias, which the BA junction, AB junction and the CB junction. Both are in forward bias saturation. AB junction is forward bias and CB junction is in reverse bias. And also inverted or inverse active region, reverse and the forward, cutoff, reverse and the reverse. You can easily understood here. And also if you see that the operation of the NPN transistor, here how the electrons are injected from N to the P and P to the N. And also here you can see the base emitter junction and the base collector junction. The base emitter junction is width is small, whereas the base collector junction width is large, because here we can see that the potential we applied, that makes the difference in the operation, where we here the RE is the emitter resistance and the RC is the collector resistance. During the active mode, the base emitter junction is in forward bias and the base collector junction is in reverse bias. Hence what? Since the BA junction is in forward bias, electrons from the emitters are injected across the BA junction into the base. If you see that the further, once the base region, the electrons are quickly accelerated through the base due to the reverse bias CB region, right? Here this is the CB region, reverse bias, and here we have the forward bias. Some electrons in passing through the base region recombine with majority carriers holes in the base. This produces the current at the base. I will illustrate the small animated picture in the coming slides. You can see that here. Here this is the emitter region, there is the base region, and here is the collector region. Right? Imagine that these are the marbles which are sitting here. Right? Imagine that the marbles are the electrons. The flat is the base region with the gaps where the marbles may fall or trap in recombination. Here these are the gaps, right? These are the gap you can try to understand. The slope of the collector region represent high electric field in the CB region. High electric field in the CB region, right? Why high electric field in the CB region, right? You need to see that the CB region, right? This region we are talking about it. This region is highly reverse bias. Highly reverse bias. That's why the high voltage has been applied that brings high potential. High potential. High potential. You can see that. I'll try to understand. I will try to explain this illustration. We are imagining that marbles are the electrons, and here the marble has moved up. The reason behind is that we applied some base emitter voltage, which is the forward voltage has been applied. When this voltage is applied, the electrons get some energy. Hence, when enough energy is given to the marbles, they will be accelerated towards the base region with enough momentum to pass base and straight flight to the collector. Just we are pushing the electrons into the emitter to the base region. Now try to understand here. See the illustration here. Whereas we applied. Now we can see that here one electron has fallen into the trap or recombined with the participated in the recombination, and you can see the flow how the electrons are moved. You can see, I'm repeating again. See that, try to observe here how the marbles are moving. See that the speed, how the acceleration has been increased at the collector region. That is the reason we can see that the collector is where we are getting the amplified current at the output side, right? The marbles are moving from the emitter to the base to the collector. At the base, we can see that the recombination, that is the IB current is falling here. IB current, where you can see that the IC current, here we can see that IA current, right? This is the way we can understand that the transistor illustration. If you see the mathematical expressions for this, the IA current is equal to IS into VEB by VT minus 1, where VT is the threshold voltage, we can say. The VB is the base emitter voltage. IS is the saturated current. The KVL we discussed, IE is equal to IC plus IB. The number of electrons cross the base region and they direct into the collector region is a constant factor. That factor we call as the beta factor of number of electrons existing the base region, that we call as the number of electrons reaching the collector region is directly proportional to the number of electrons injected or crossing the base region. That's called the IC is equal to alpha times of IA. So also alpha is a current gain in common base configuration, where beta is a current gain in common emitter configuration. And ideally you can see that the alpha will be generally unity or maybe less than 1, which may be in 0.9 to 999, whereas beta will be varies between 50 to 250. Here you can see the KCL. The IC is equal to beta times FIB. If you see the relation between these three, as we have seen that the IC is equal to IC plus IB, just we are substituting IC is equal to beta times of IB here. Now you can see that if you find out the relation between the IE and the IB, IE is equal to beta plus 1 times of IB, beta 1 times of IB, and with IC is equal to beta times of IB, IB is equal to IC by beta, and we can see that the relation between the IE and the IC is equal to IE is equal to beta plus 1 by, right, the beta plus 1 by beta, right. If you simplify the terms, the terminology, if you rewrite this one, we can get IE is equal to IC is equal to IE times of beta by beta plus 1. Comparing the IC is equal to alpha times of I, there we can write alpha is equal to beta by beta plus 1. This relation is very important in order to understand, in order to solve certain problems in the biasing. You can also see that the operation of the NPN transistor same as PNP transistor, earlier what we discussed. Here only the majority charge carriers plays the major role. Minority charge carriers also plays crucial role. Same thing here, the active mode we can try to understand that how this diodes are structured. Earlier diodes are structured, these diodes are structured. Two N's are connected together to form a PNP, right? And here also you can see that the current equations as already we discussed, just I am going through it. Here we notice that VEB instead of VBE. The same relations also you can see that. These are the very important. Here we can see that as we discussed today, the basics of the semiconductors, the importance of the BJT 3-terminal device. We have seen clearly the job of emitter, base and the collector, and also we have seen that Kirchhoff current laws in a BJT and the voltage line in a BJT. Further we have seen the construction of a BJT and working of the BJT. If you see that the simple relation comparison to the NPN and the PNP transistor, EA, emitter current is equal to, right, both the currents you can see that IC is equal to beta times of IB, IC is equal to alpha times of IE, whereas IE is equal to IB times of beta plus 1, and alpha can be represented as beta by 1 plus beta, whereas beta can be rewritten as alpha by 1 minus alpha. This relation is very important to solve certain problems, to find out the currents. If you know any of the two currents, you can determine third current. If you know any of the two currents in a transistor, you can find out third current easily. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.